Okay, today we're going to be looking at topography. Topography is a way we can actually represent a three-dimensional Earth on a two-dimensional map. So you can fold it, stick it in your backpack, your back pocket, your glove compartment, whatever. And basically what we're doing in topography is we're actually working with elevations that have been determined by lots of different ways. I guess now it's actually done by satellite, but used to be done by measuring with a Jacob staff and actually going from one position like sea level and finding how high everything is in reference to it. Everything is again based on how far above or below sea level it's found. But basically what we're trying to do is we're trying to connect points of equal something. This is actually something for meteorology, which I showed my kids earlier this year. This is talking about isotherms, temperatures connecting with equal lines and colors. I'll show you this website in a couple minutes. But basically what we're doing is, like, if the 80 line's down here, we start with an 80 and we move over and we try to keep all the 80s inside. Anything less than 80s on the outside, anything more than 80s on the inside. If it's less than 80 but not by much, it goes really close. If it's farther away from 80, like 75 to 85, goes in the middle. I'll do the 60 line also. I see a 60 right there, so I'm going to keep 60s inside, really close to a 61, not so close to a 65, 66, 68, 69, and a 70 goes there, and then keeping 60s inside. Something that looks about like that. Let's go ahead and go look at this website. Here's the website, and when you get to here they actually give you a pen. I'm not going to draw them this time. I'm going to actually have it draw it. So we're going to draw the 40. Actually, let's do the 40 line. 40 comes in someplace right around here, keeps the 38 above, 40 in that direction, goes up, goes over to that 40, goes down to this 40, goes there, over to that 40, really close to 39, really close to the 41, and farther away. And you can actually have them draw the 40 line. And you can see theirs is a little smoother, but we got just about the same place. We can draw a 50 line. We can draw that 80 line that we drew earlier. You can actually have hints put on there, so it's saying that they stay in between. You can show all of them, and then you can finally colorize them. And this is what a regular isotherm map looks like, but topographic maps are going to look pretty much the same. Okay, so I had my kids work with a couple of YouTube sites actually through the New York Regents exam. This one was actually how to determine the lowest possible elevation. Well, first you look at the map. This is what it would look like if you looked at the side view of the topography. This is the topographic map, the two-dimensional representation of this relatively three-dimensional object. You can see it's got a little pit inside of it, a depression, and that's actually shown by a special kind of contour line. But anyway, they don't tell you what these elevations are in, so we're going to say they're meters. It doesn't have the little tick mark for feet. But what they've done is they've connected every point that is 10 feet, and 10 feet, and 20 feet, looking like that. And this one also is 20, connecting with the line. Okay, so lowest elevation. If that's 10, that's 20. Lowest elevation's got to be over in this location. I'm going to guess like right there. I'm also going to guess like right there. I can also guess like right there, because that's less than 10. It's in that depression. This one, the line that would be on the other side of it would be 0. I would say this one's probably closer to 0 than the other two. I'm going to say my lowest elevation is right there. Okay, 7 laws of a contour line. We have contour line must connect points of equal elevation, separating points higher elevation uphill from lower elevation downhill. If you look at this 30 and 40 meter line, that 40 connects points of equal elevation. It separates points higher uphill from points lower downhill. Change in elevation between any two consecutive contour lines has to equal the contour interval. The interval for this map is 10. So if I go from any one to any other one, uphill or downhill, I'm either going up by 10 or I'm going down by 10. Contour lines never cross. You can see that they can get closer together, they can get farther apart, but they can never cross. And why not? Because you can't have two places that have two different elevations. There is a couple of rare cases, an overhanging cliff where the rock actually sits over a cliff may have this, but they'll actually show that with text writing on there as well. Otherwise, the reader can't make it out. Contour lines are always closed loops. You can see they always close in on themselves. The question is your map big enough? You know, it's the 30, the 40, the 20, and the 10, but this 20 goes off the map, comes back on the map, goes off the map, comes back on. Map's not big enough to show all the lines. Spacing between them gives an idea of the area's slope. The closer they are together, the steeper the slope. The farther they are apart, the more gentle. Depressions are represented by hatched marks on contour lines. Hatchers always point downhill. These are these little teeth on there. They're always pointing downhill. The first hatcher line is always equal to the last regular line downhill. So if you take a look at this, it's right next to this 30. How come those two elevations are different? Because you're climbing out of the hole to 20 and you climb out of the hole to 30. That's not the downhill side. Go back down into the depression, come back up out of the depression, go up a little bit and you come back down, and that 20 is the downhill side. 20 and 20, that's equal to the 20. It's equal to the same elevation as the downhill side. Contour intervals appear on both sides of an area where slope reverses direction. If you take a look at this 20 and that 20 right there, if you're walking this way, you're walking uphill a little bit, and then you walk back down. Two lines the same elevation showing you a reverse in the direction. Same as with this 20 and that 20. You're going downhill. You got to come back up to get to the 20 again. So you're reversing your elevation. You go down into it and you come back up. Okay, map number 2. How do you tell the highest possible elevation? Well, you look for not the smallest number, you look for the biggest number. Now, contour interval on this map, again, it doesn't tell you if it's feet or meters. We'll assume that it is meters. It does have 900 there to 1,000. It looks like it's 100. It does have 1,000 to 1,500. This is called an index contour because it actually has that number written on it. That 900 is there for convenience, probably because of something that's on the map close to that. But if you count these, it's 1, 2, 3, 4, 5 lines in 500 feet, so each one is worth 100 meters of elevation. When the circles get smaller, you're going to higher elevation. Circles get bigger, you're going to lower elevation. How do you find the highest elevation? The highest elevation is this smallest circle right there, and probably the point right in the middle. I'd have to guess that X probably is the highest elevation, but usually you would assume it's in the middle unless it's given something like that. And they do like to mark the tops of the hills with specific elevations. How do you determine steep versus gentle slope? You take a look at the spacing between the contours. If you look at, you're climbing from A up to this 130 feet, 130 feet elevation, or you're going from B up to the 130 feet elevation. You go one way, your friend goes another. Who's actually got the steeper climb? Who does the most work? Well, in physics, they'll tell you the work is the same because you start at the same elevation. That first line away from the ocean, which was 0 elevation, there's 100, so 20, 40, 60, 80, 1. It's 100 divided by 5, 20 feet per line. It even tells you right there. So there's 0. This one would be 20. This one would be 60. That one's 100. There's 120. So the next line would be 140. Doesn't get up that high. So this is 134. Steeper on this side because the lines are closer together. You're going a smaller distance, but you go the same number of lines if you're going this way. So lines closer together, steeper. Lines farther apart, even more gentle. What happens if you walk in between, if you walk parallel to the lines? You don't change elevation at all. So you could walk around that hill and really not do much more than just walk in a straight line, even though your body may be leaning more on one side than it was the other, and you may get your feet wet by going through this creek. Oh, there was a line, there must have been one up here. I didn't do number 7. Contour lines cross a stream or valley, they form a V shape. The V's don't show in either one of these, but it does show in the one where we just were. Here comes this stream that is cut, taking away sediment away from this island, dumping it into this ocean, and it actually cuts into the mountain, making that river valley. Everywhere you'd expect this contour line to go more like this, well, it doesn't. It actually does make that V shape, and that V shape points uphill. So if you can find a V in a map, you can tell that it's moving uphill. How do you tell what direction streams flow? Well, those V's again, they point uphill. So stream flows from basically higher elevation, you can see the numbers right there, to lower elevation. Water's going this way. How do you draw a topographic profile? You set up a line, and they actually, let's see if they did the same one as the one that was up here. Yeah, they set a line from that X to that Y, and they want to draw that, probably because it's got this little hill, it's got this little depression, it's got all that little stuff in it. So we go back down to this one. We put a piece of paper on top of the line that we want to profile. We put a mark everywhere a contour line touches the paper. So they said this was X, and they said this was 10. And then there is 20. And this one right here, if you remember, that's also 20. Right there, 10. Right here, another 10. Contour lines connect points of equal elevation. There's another 20. This one, if you remember, was the hill. That's 30, 40, 40, 30, and they actually put that right on a line. If we did move over a little farther right there, we can go ahead and say that that's 20 again. What would that elevation be? Doesn't have a 10. 10's down here, somewhere around 16. And again, we didn't have any feet. This actually does say elevation. In this case, it's going to be feet. So it does say on the topographic line. So the next thing we do is we pick a different color. I'm going to pick red. And we go down and we actually say that X is at the 10 point. So I'm going to put a little dot right where that is. And then here's 20. I'm going to go down and put a little dot where that 20 would touch. And what you do is you'd bring the paper down and you'd actually line it up. I can't do that with this particular program. Here's another 20. Here's another 10. Here's another 10. There's another 20. There is a 30. Whoops. There's a 40. And another 40. And another 30. And another 20, which is what they're saying is right there. Okay, now there are a couple places we probably ought to find the elevation, just because we don't know what we do between those 2 points that are the same elevation, those 2 points of those 2 points. So what would be the elevation of that point right there? What would be the elevation of that point right there? What would the elevation of that point right there be? Well, we walk from 10 to 20 uphill. We're going to walk up a little bit more. Let's say this thing is 25. Here we go down from 20 to 10 into a depression. We don't go down to 0. Let's say that also is 5. And then we're going up here to 40. We go uphill a little bit. Let's just for a grin say that is 45. So now we actually have our line. I'm going to pick a gray color to actually draw the line. Don't really have brown. And what you do is you just connect it now. Think about smooth. Mother Nature does smooth. And go up and get that little 20, 25. Go back down into the depression. Go down to the 5. And I'm hoping you guys can connect these lines better than I can. It's tough moving the hand on this bamboo pen, touch pen thing. And down, and down. And if I really was going to go all the way to the end here, I'd take it down to 16, because that's what we said the elevation was. So we go down to about there. So you can actually see that that line that would be right about here. You walk uphill, you walk downhill, you walk uphill, and then downhill a little bit, and we should probably have that. Actually, it doesn't really show in our map there. It does show there because we'd walk up a little bit and then we'd walk back down. We'd probably have another 20 and another 20 and with another 20. But we'd walk up, we'd walk down, we'd walk up, we walk up, we walk down, down, and then finally off the map. Second to last thing is this, where we calculate gradient and slope. Gradient is change in elevation, so the change in field value. We're going from x to y or y to x. We're walking downhill or uphill. Remember, smaller the circle, higher the elevation, divided by the distance. Well, they gave us a nice little distance of a mile there. I'm going to assume that also is a mile. We probably should really put a piece of paper and measure it, but I'm going to say this is a change of, let's say we have 100 units there. Doesn't really say whether it's feet. I'm going to make it feet. I'm going to say down here, contour interval is equal to feet. Okay, so that's 300 feet, that's 400 feet, and that's 1, 2, 3, 4, 5 lines. 100 divided by 5 is 20, so this one line right here is 320, 340, 360, 380. We're going from 300 to 380, so we have a change in elevation of 80 feet. Our distance is 1 mile. What's our change? Our gradient slope is 80 feet per mile. So, not a real steep slope. Change in that is not very steep, but you would be walking uphill, you'd feel it, and downhill. Last thing we have to talk about is latitude and longitude. A couple of lines that we need to know. This line that goes to this little tick mark of South America goes underneath this part of Africa. This is our equator, 0 degrees. Everything above that is the northern hemisphere. Everything below it is the southern hemisphere. This line that goes through Great Britain, this is our 0 point. This is actually defined by halfway through the north, between the North Pole and the South Pole. It's geographically defined. This one was man-made. We're not going to go into the whys, but basically this is the man-made. This is understood worldwide as being 0 degrees longitude. That makes this the western horizon. This is the eastern, hemisphere. This is the eastern hemisphere. Got a couple more lines which are important in terms of season. This is the Tropic of Cancer. Sun's northernmost migration on its apparent trip due to the Earth. It's 23.5, equal to the flip of our axis, 23 degrees north of the equator. This is the Tropic of Capricorn, which is at, you can say negative 23.5 or 23.5 degrees south, and you got to put the degree sign. Okay, with this we can actually place our position any place on this planet. These are in 15s, and the way you can tell that is 15, 30, 45. Just keeps moving up and up and up and up and up, and same thing here, and then we go 30, 60, 90, 120, 150, 180 would be over there, and same thing for that. So if we wanted to figure out the latitude and longitude of that point right there, all we'd have to do is say it is 15 degrees below the equator, so that point, let's say that's point A, and you always do latitude first, 15 degrees south, and it is 1, 2, 3, 4, 5 times 15 degrees by 75, I think. 15, 30, 60, 75 degrees east. Okay, so you can find any location on the planet based on latitude and longitude. Okay, that should do it. Thank you much. Bye.